Olá, pessoal. Boa tarde a todos. Mais uma vez, muito obrigado por vocês estarem aqui e assistirem essa apresentação de hoje, que vai ser muito interessante, tá? Então, nós vamos falar sobre engenharia, principalmente voltada para a área de engenharia aeroespacial. E, para isso, nós temos o professor DeWalt e a Andy, tá? Da Universidade de South Carolina, mas eu já vou passar a palavra para eles. Então, para vocês que não conhecem a GoTesso é uma empresa especializada em auxiliar vocês, brasileiros, a entrarem em universidades mundo afora. E para quem ainda está aí do 9º ao 2º ano, nós temos um programa de preparação, de mentoria, que se chama Eu Global, e esse programa que a gente está fazendo agora, que são essas masterclasses, fazem parte desse programa do Eu Global, que a gente faz uma mentoria, a gente auxilia os alunos a estarem prontos para as faculdades no exterior quando chegarem no 3º ano, tá bom? Então, eu vou mudar agora a chavinha para o inglês. So, I just wanted to thank you, Professor DeWalt. Thank you, Angie, for being here today with us once again. And I'm really glad. I think this is going to be a great presentation. And Angie, I just wanted to pass the word to you.
Great. Thank you very much. Hi, guys. My name is Angie. I am the Student Success Manager at University of South Carolina, the International Accelerator Program. And over here, we have Dr. Wout de Bakker, who's also my husband. He is a professor in the mechanical engineering and aerospace engineering. So a lot of my students who come here for an engineering degree sometimes would take classes from Dr. de Bakker before they graduate. And then I'm going to pass the microphone to him, and let's learn some things about aerospace engineering.
All right, thank you very much. It's an honor for me to kind of bring you up to speed in terms of what we're doing here at the University of South Carolina, and maybe figuring out if aerospace engineering is something that you're interested in, or is something that you really don't really care about. So hopefully throughout the day we will this session of the next 20 minutes or so, we'll learn a bit more about that, and it'll also give you a bit of an idea of what it means to take an aerospace engineering class. So yes, it is rocket science, but no, it's really not that hard. It is a lot of work though, so you'll just have to get used to that part. So what I want to do today is go over what the main aerospace engineering field is like, what aerospace engineering is, what do we do in aerospace engineering, what can you do with that degree, what challenges we have, why we already have planes, so why do we need aerospace engineers, what's important about that, and what can you do with this degree, right? So what can you do that really sets you up for the right career, for the job you like, for the type of field you enjoy, and hopefully for a challenge that you want to take in the world. So at the end of this talk, I'll also show you a bit about what we're doing at USC, at University of South Carolina, in terms of aerospace engineering, and what that could mean for you if you decide to join us here. So before I dive into it, though, I want to give you a bit of a background about who I am. So I started my aerospace engineering journey very young. When I was about 7 years old, I was already very enthusiastic about everything that flew, everything that was machinery. And so in 2007, I started my aerospace engineering career at the University of Delft in the Netherlands, and then I graduated in 2010. And part of my graduate program or undergraduate program was working on a new design for Airbus and to carry large aerospace structures. So throughout today, I'll show you a lot of different parts about aerospace, parts that I've worked on and parts that you could work on in the future as well. So during my master's, I decided, okay, the bachelor is fun, but let's do something that gives me a bit more detail on my studies. So I dove into composite structures and manufacturing of aircraft. It really clicked with me to go from something that was an idea to a design, to a product, to a part, to something that actually flies, right? So in my undergraduate and graduate studies, I dove deeper and deeper into the parts that I really liked, and which for me was aircraft design and composite structures manufacturing. So I did my thesis in micro buckling, which is a really complicated way of composite failure. But I also knew nothing beforehand, so you get introduced to these concepts throughout your career. And then later, I joined Alpha Star Corporation for 2 years in Long Beach, California, here in the US. And I was working on simulating impact and crash dynamics on a larger aircraft, but also impact on smaller aircraft, and looking at how composites behave or shape when something hits them, and what happens when you hit a piece of hail, or if you hit a structure, what happens to the aerospace and the aircraft. How can we make an aircraft that's still safe and flies the way it's supposed to fly, even though we may have some damage by hitting a bird or hitting some hail? So this was during my 2-year-long internship in Long Beach, and then finally I started my career at USC in 2014, which is now a little over 10 years ago, where I obtained my doctorate in mechanical engineering, then became a postdoctoral researcher. Now I'm an assistant professor, and I teach in our aerospace engineering program on aerospace systems, senior design, and aircraft design. So throughout my studies here, I've had the fortune to work with a lot of different companies, all the way from equipment manufacturers, where we designed and built and produced a brand new type of 3D printer for aircraft parts, but also working with a lot of students, right? Anywhere from high school students all the way through doctoral students like myself at some point. So that's me. That's me here. Hopefully you can see my mouse here on the left side when we were taken into the final design step of this equipment here, where we did some manufacturing of a large 3D printer. Right here, I'm in the middle with my team a couple of years ago, and this was with my team in 2022, right after the pandemic, or right around the pandemic timeframe. And again, right, there's room for everyone on the team. We have a lot of different backgrounds, a lot of different people that are interested in this. And really what I'm asking from my students is that they are motivated, that they were self-started, and that they are eager to learn and put in the energy that's required. So what does that now mean for the today's content for the aerospace engineering and design? So maybe you have already a good idea, maybe you have no clue at all. What is aerospace engineering? Now, I see we have some people on the call here today. Maybe one of you has an idea of what it could be to be an aerospace engineer. What do you do? I can't really see the people here, but feel free to speak up. We'll put something in the chat.
Hi, can anyone hear me?
Yes, Peter, go ahead.
Oh, great. So I think that aerospace engineering is when you design and develop aerospace vehicles like the plane, the airplane, or the rockets, or something related to that. Is it?
Absolutely. Yes, that's very true. So designing rockets, designing planes is probably the easiest thing to think about, right? So that is, if you tell people, okay, what is an aerospace engineer? Well, we make planes and rockets. So you may see something that looks like this, right? So we come up with these cool drawings, cool renderings, and some of these, they're real, some of them are very not so real, right? So you see here perhaps something that could do the next generation of passenger aircraft or the next generation of cargo transportation. Maybe think of a big cruise ship in the sky type of concepts. All of these are ideas that we come up with, and then there's two things we need. We need a lot of money to make it happen, and we need smart people to make it happen. Now, usually aerospace engineers are not the ones who bring in the money, but they are the ones who make it happen on a technical level, right? So if you think you like a technical challenge and you have some friends with a lot of money, you can make a lot of things happen. It's also a lot more than things that just fly, right? So think of not just in air, but it's also things in space. Here are some very famous pictures over the last 5 years or so of brand new designs that happen in aerospace on a daily basis. Think of brand new launch vehicles to bring new satellites into orbit. Think of new types of telescopes to look into distant galaxies and to explore the universe. or orbital laboratories like the International Space Station here on the bottom left. And we try to push the boundaries every day. On the right side, probably the most expensive selfie you'll ever see. This is a couple $2 billion of a Mars rover that is on Mars. It's the size of a sedan car, so a standard size car. And it's taking a picture of itself. And you can see it's dirty, it's grimy, it has a lot of dust on it. Some of the wheels are damaged. So we've put this car on Mars, and then we make it take a picture of the environment, but also of itself, to see how it evolves over time and how we can make these things last, so that when people eventually do go to Mars, we will have an idea of how to survive the harsh climate on Mars and how to get back home. So you see this third picture here. This is a picture from a test flight that was done just a couple months ago by SpaceX on bringing a essentially 20-story building back from orbit in one piece and trying to land it too. These are insane challenges, very complicated designs, and very, a good designer makes the design look easy, but it is absolutely anything but easy. So the real question you may have now is, okay, this sounds amazing. How do I get started with this? Well, design as a concept is a discipline on its own. Just like you have a lot of different fields you can study, designing is something you can study for a while. And the major question we ask ourselves is, if we don't know anything about our vehicle or our design, where do we start the design? And you see here on the diagram on the right, this is one literally taken from one of my classes that I gave a couple weeks ago. We have requirements. What does the design have to do? We have trade studies and sizing studies. We have a concept. We have an analysis. We need to go back and forth and optimize the design. And really, where do we start? Well, the answer here is, it depends on who you ask. If you ask someone in the banking world, they will say design starts with money. If you ask the customer, they will say, well, the design starts with how many passengers I want to carry. Maybe the sizing specialist will need a certain weight estimate, or maybe the government will say, well, design starts with regulations. And really, as a designer, you think, well, maybe I start with a concept, something that I want to bring out. And the true answer here is design really starts kind of everywhere. It starts everywhere at once. But it's kind of similar to looking through a camera that is not focused. I know many of you have phone cameras now, but even on phone cameras, you can set the focus to be very fuzzy, just like in the image here. And as you become clearer about your design, as your design becomes more sharp, it becomes more real and it becomes more true. So just like dialing the focus on a camera, at some point it's very blurry, it's very fuzzy, it's very cloudy, but at the end of your design process, you see a sharp image, you have a clear vision of what you want to achieve with your design. So in my classes, for example, this class on engineering design, it's not just about learning how to draw an aircraft. It's also learning how to design an aircraft. So doing the math, doing the statistics, and of course also a little bit of how to draw an aircraft. So we get familiar with the design process. We learn how to move into uncertainty, which is really the key of design. If you ever are overwhelmed, or if you are ever thinking, okay, what do I do first? I have so many things to do. Designers love that. They call that, not being scared of having open-ended problems, having ill-defined or poorly defined problems, because all of that is part of design. And as a designer, you think that's fun. So you think design is fun. So if you see like you have too many options and you have too many things you could be doing, well, that's the fuzzy cloud. How do we go through iteration on iteration to make it a little bit more sharp so we know exactly what we need to do on our next step and come up with a real working design? So we integrate everything we know at this point, everything we've learned throughout our life, throughout our engineering life, but also throughout our high school lives, and anyone we know as friends, we will ask them, what do you think of this design? How do you make this into something real? And we build a framework, so we build a roadmap based off of all the different disciplines that we know of, for example, structures or aerodynamics or systems, and we turn that from a concept, something that looks like this drawing right here, which, I mean, if you've drawn an aircraft before as a in school, or as a doodle when you're supposed to be paying attention, it probably maybe looks something like this. Well, that's the idea. How do you turn that into a design? Well, that's where the engineering design process comes in. We turn it into blueprints, we become the architect of our dreams and build it into something real. So that is the main design process. I know this is only a couple slides of introduction of aerospace engineering design, but it gives you a bit of an idea of the type of topics we talk about. And of course, after a while, there's a lot more equations, but we're not going to do that. I'm not going to do that to you. I'll show you one equation today, and that's all. So as an aerospace engineer, now that you have a bit more of an idea of what it means to be a designer and an engineer, let's look at some key fields of study that bring this all together. And in the background here, I will try to include as many pretty pictures as possible. You see what it means like when you have a good design. You can make a lot of different aircraft at the same time. It's almost like building cars where you make one after another and after another. The big difference is that the quality of each one of these designs and each one of these products must be safe, because we all know the news will get really aggressive if we start making mistakes as aerospace engineers, right? So immediately a lot of people's life could be at risk. So when we bring all those fields of study together, they all have to collaborate. And more than any other discipline, aerospace engineering is about finding compromises between all the different parts of a problem that you're trying to solve. If you ask someone who does aerodynamics, what is the best airplane, they will give you something that looks like this airplane here. Oops, let's go back. This airplane here, which is all very sleek and very sharp and looks very aerodynamic. But if you ask someone who designs the engines, they're like, well, let's put the biggest possible engine in it. We love big engines, so let's make it go fast. Or someone who designs the electrical system will say, we need all the electrical system to power everything. But it's really not one or these or the other. It's a combination of everything working correctly together, interfacing correctly together, that gives us a good quality, coherent design. So some of the fields of studies that you may see in aerospace engineering are related to aerospace structures. So you think of manufacturing, fabrication, of an aircraft, and analyzing the structure, testing it, doing fatigue and fracture mechanics, seeing how long the aircraft will live, at what point we need to start replacing parts of the aircraft, doing a stress analysis or a load analysis, and selecting the right materials and defining new materials that work for our designs. So in the background here, this is not something you would like to see when you're flying, but this is the Boeing 787 that's made here in Charleston, South Carolina, and it's going through what we call an ultimate wing load test. So we pick the airplane, the middle of the airplane, and we tie it down to the ground, and then we lift the wings up as far as possible to see at what point they break. And they can't be too strong, because then it means the aircraft will just be too heavy. And they can't be too weak, because then, of course, we have to redesign the aircraft. So it has to break at a certain exact percentage of deflection here from the ground. And that's what we do. I always like to joke that as an aerospace engineer, we try to make things that just don't break, or don't just break, right? So that what that means is we make things that are designed to break at a certain point, but usually that point should not occur during normal parts of the aircraft's life. Other parts of this may be flight performance and propulsion. So think of dynamics, looking at weight and balance. Where is the center of mass? What is this? How much thrust do we need? What does the airplane performance look like? The stability and control characteristics. Can we fly the aircraft? Can we land the aircraft at low speed? Do we know what the equations of motion are? How is it going to behave throughout its life? How is it going to behave when we fly through a storm? Do we need special computers on board that can help us navigate through different weather events? And of course, power, right? A lot of aircraft is designed is around the engine. So thermodynamics are going to be a big part of that. Heat transfer between the hot combusting fuel and the fuel tanks themselves. Because what is a rocket? But just a fuel tank on top of a nozzle. Looking at rocket engine design and components, propellants and combusting. How can we get the best performance out of our fuel so that we can carry less of that fuel, and optimizing the weight as much as possible. Think about new concepts. Propeller engines, turboprop engines, combustion engines, gas turbine engines, electric engines, hybrid propulsion techniques, All of that ties into strong backgrounds in physics, in thermodynamics, in knowing what energy we put in and what energy we put out, and how little losses we can have along the way. So we're looking at new types of propulsion for aircraft. In particular, electric and hybrid propulsion are now at the forefront of the development. But then in space, we're looking at what is the effect of the space environment? What communication systems can we have? We all use GPS now or something similar to it on a daily basis. That had to be put up there at some point. What kind of electrical systems do we need for space systems? And how do we make sure that our satellites don't fall out of the sky, right? So the orbital mechanics and the planetary science we can do from space can help us predict the weather, can help us predict forest fires, or can help us deploy emergency personnel to disaster sites, for example. And all of that requires spacecraft design and spacecraft systems engineering, which is something an aerospace engineer would do when they're working in the astronautics and space field. Finally, I have an example here on aerodynamics, where, of course, a lot of what we do is flying through air or through denser materials. So compressible flow, experimental methods, flow behavior and boundary layers, wing theory, aerofoil theory, these are all topics that you will learn as an aerospace engineer if you're interested in this. And there it is, there's one of the two equations for fluid dynamics here, telling you about the Reynolds number, which is really just a scale number to say, well, if I can make the aircraft smaller, does the air still behave the same way around my aircraft? So I know I'm throwing a lot at you now. So it sounds like with all the pictures that I've been showing you that, we've figured a lot of this out already. So what is there left to do in this field of study? There's a lot that we're trying to still do. And unfortunately, it doesn't always go right. So here in the picture, you see the images taken from the Challenger disaster in 1989. And unfortunately, this was just one of the examples of what can happen if something doesn't go right in the aerospace engineering world. They say that aerospace engineering is easy. It's like riding a bike, except the bike is now on fire and you are on fire and everything else is on fire. So how do you get through a challenging design problem here so that even if everything is on fire, you can still survive your mission, right? So we are trying to solve the next generation of aerospace problems, and that means environmental impact and sustainability. How can we make aircraft less polluting? They are flying very high up in the atmosphere and they're dumping a lot of fuel. So how can we make that give us the best possible performance?
And this is a Brazilian airplane, right?
Yes, this is, I believe, the Embraer business jet.
Legacy.
So yeah, has a very big legacy in Brasilia has a very strong aerospace field as well. So and very popular nowadays. Business jets are once again booming for a lot of classes of people. So how to make them cheaper, how to make them more efficient, how to make them safer and more reliable. Different propulsion systems, think about electric propulsions or hybrid fuel cell technologies, maybe making some aircraft unmanned. So how can we observe sites without having pilots on board? One of the parts that we are working on here at the University of South Carolina is, for example, urban air, advanced air mobility. So you may have seen concepts like this Joby air taxi, or Whisk Aero has a similar design. I believe right now there are over 1,000 different concepts in development related to this type of technology. So the air taxis are coming. It's just a matter of who of those 1,000 designs, and I'm sure there are some in Brasilia or in Brazil who are doing the same, who will survive this big design challenge that we want to have an efficient aircraft that uses low noise, low pollution, and can carry us from A to B very safely. Right now, a lot of these roles are taken up by helicopters, but helicopters are noisy. They have a lot of maintenance requirements. So this seems to be the next generation of helicopter and short aircraft or short distance aircraft. But that's not everything, right? We're looking at the next generation of aircraft. Blended wing bodies is something we study here at the University of South Carolina. We're also working on a next generation of hypersonic systems. Fortunately, I can't say too much about those, but these are all public images. And you can see some of the work that we're doing in terms of catching parts that fall from space together with some of our space suppliers here. So if you want to be part of these developments, then what is the next step for you, right? So you are high school students, I take it, or at least maybe thinking of transferring. So what is your career path and your opportunity? How can you be part of this ecosystem of what I think is the most exciting job in the world, which is why I'm doing it? So potentially you love aerodynamics and you want to learn how to design the next best aerodynamic aircraft. Or maybe you want to become an aircraft designer. That's more the role that I'm in these days. Or if you love engines or propulsion, you can learn the next generation of engine design and propulsion engineering. Or if this is too much aeronautics for you, but perhaps you want to do more on the space side, right? So payload integrations, spacecraft systems engineering, launch vehicle design, thermal systems, orbital mechanics, all of these require people that need to bring us into the next generation of development. And where do you find jobs after graduations? Well, it turns out that if you know how to design a rocket and an aircraft, people really like you and people really want you to work for them. So you can work almost everywhere. Aerospace suppliers, manufacturers of aircraft and satellites. You can work for the government and legislation, either here in the US or abroad. And every country worldwide has positions that relate to aerospace design. Research and development, as I showed you, we are doing a lot of work on the research and development side. And of course, you can always start your own company as well. Defense is, I don't think I have to go into the details of the global geopolitical climate, but there's a lot happening on the defense side and on the space agency side. And of course, if you are, if you're regarded as an aerospace engineer or rocket scientist, the finance and consultant fields are always looking for people who know how to do very complex problems and how to design their way out of complex situations. If you're more on the operational side, you may think of all the different airlines or all the different airports you could work at, tourism industry, and so on and so on. So this slide, I'm sure the slides may be shared with you afterwards. I can send these to the team. So you can dig through these a lot more. None of this is secret material. Now, I wouldn't be doing my job as a professor at the University of South Carolina to at least tell you a little bit about what that means for our students here, right? So now that you know what the aerospace engineering field is and what we do, how do we approach that challenge here in Columbia, South Carolina? So our primary offerings for our undergraduate students is an aerospace engineering bachelor's of science in engineering, or mechanical engineering, bachelor's of science in engineering. Those two will get you the closest to the aerospace engineering field right away. Of course, you can also, if you do any other major, you can do minors in aerospace, mechanical, or nuclear engineering. If you already have an undergraduate degree, then you could think about one of the graduate programs in aerospace or mechanical engineering. The University of South Carolina its engineering program is ranked 81st in the nation and among the best engineering schools in 2025. And we have a 12-spot increase over last year's program, and it looks like we will be going up again this year. So our program is getting higher and higher ranking every year. In terms of numbers, this year we started our aerospace engineering freshman students, so the first-year students, 127 students started our freshman year. This means we are already in the top 15, if not top 10, of aerospace engineering programs in the United States. So this is really a countrywide effort, going from a very small program to now one of the larger programs in the country. And our senior year students, I think we have about 35 students that are graduating. So we do see a lot of students trickling out. It's not for everyone, right? People see the pretty pictures, but there is a lot of math that we didn't cover today. So you'll see those come back throughout your studies in aerospace. If you say, okay, aerospace is cool, but I want maybe something else, or I'm not that good for engineering, maybe something that's not engineering that still can get me into aerospace, absolutely. In computer engineering, information systems, physics, electrical engineering, environmental science, business management, policy and law, communications, all of this can be tied to aerospace. So if you want to become a lawyer, but you want to learn how to do work for the FAA and do policy-related aspects, there are a significant number of people in that field active as well. And as I said, finance is also a big recruiter for our graduate students. So There's a lot of opportunities here. You're going to prepare for an exciting career when you study design, construction, and science of aircraft, rockets, and spacecraft, right? You've seen some of the pictures. That's I think the coolest part of my job is that I get to look at those pictures every day and say, yeah, I'm working, right? So in South Carolina, we are the only undergraduate aerospace engineering program, which means I know you are mostly international students or all international students. That may not mean much, but we have a lot of students domestically as well that come to South Carolina for our aerospace engineering program. And there's some lab works where you can gain some really hands-on experience with satellites, aircraft, unmanned systems, and so on. So you see some of our lab equipment where we make state-of-the-art composites, state-of-the-art tooling for aircraft, and we work with companies like Boeing, like Airbus, like Gulfstream, and we make parts for these manufacturers, and we also train our students on how to learn how to fly, because it helps you to develop a sense of what it means to fly an aircraft. And this is all part of our state-of-the-art engineering labs, where we have wind tunnels and a whole set of FAA certified simulators that we can teach you how to fly. Now, I do have to say, I see the simulators, and a lot of you maybe played flight simulator growing up. You're not becoming a pilot here, right? Everything I've said here does not include becoming a pilot. Can you still be a pilot with an aerospace engineering degree? Absolutely, but that's not what we're teaching you, right? So if you want to become a pilot, there are different career tracks for that. If you do decide to come to USC, I would highly recommend that you get engaged or get active with some of our extracurricular clubs and societies. In particular, the ones that are the most active ones is our AIAA, which is the American Institute for Aeronautics and Astronautics. It's the largest aerospace-related professional society. So if you want to network and find a job in the field, AIAA can help you with that. We currently have about 100 students in this organization, and there's about 36,000 worldwide members. And that includes all the big ones, including Embraer. If I remember correctly, they are a corporate member of AIAA. The Society of Advancement of Materials and Process Engineering tells you everything you need to know about how to make composites and how to make high-quality composites for aerospace. And for example, if you like more of the space side of things, you could think about joining the Rocketry Club, or maybe even if you want to learn how to fly, our flight club can help you with that. And at the end of your degree, and if you've done your homework well, you'll be able to design parts that look like this, right? So here are some examples from students in my class who've designed new concept of aircraft that all should work. Of course, we don't have the budget to build the actual ones, but on paper, these designs all work. And in your senior design, which is one of the courses I teach, we also cover a full design project from start to finish, where, for example, you can make a rocket booster on a small scale, or you can make a little drone, or you can make a rover to explore another planet, of course, at a much smaller scale. But the whole project goes from idea to concept and to prototype within one semester. So if you want to learn more about and look at what previous students have done, have a look at this QR code here. That'll bring you to the website on how our seniors are doing for senior design. So hopefully this has been a good background for you in terms of what we do here at Engineering and Computing in South Carolina, what our key fields of study are, what we do, and what you can do with the degree. And I'd be happy to answer any questions if you have any. Thank you so much.
Thank you very much, Professor. Yes, Bernardo, go ahead.
Hello. First of all, I would like to introduce myself. Hello, my name is Bernardo. I'm a 11th grade high school student. And I gotta say that I don't have much experience in aerospace engineering, and my overall experience could be summarized into some like physics Olympiads and like a NASA Space Apps Challenge or something like that. So
Sure.
Because of that, I would like to link with my overall interests, which is technology and business. So I'd like to ask, how do you see the integration of AI and some ascending technologies in this field, and how do you nowadays use in your current daily lives?
That's a great question. Thank you, Bernardo, for asking that. So the way that, when I was going through school 20 years ago, I know I sound really old saying that, but they were always telling me, well, you'll never have a calculator in your pocket, so you have to know how to do math, right? So guess what? I'm carrying this one around every day. I have, I don't know how many kilobytes of battery power and calculating power. So the way that that the field is looking at AI is, first of all, it's everywhere. We are still trying to figure out what it would mean for us. But I can tell you already that on every level of design, engineering, execution, operation, maintenance, every part of that is tied to AI or being tied to AI. Now, there's some goods and some bads to that, but I think overall, just like when we switched from hand calculations to pocket calculations, or from handwriting to typewriters and then computers, AI is an accelerator. It'll take what we already do and make it faster, make it hopefully better, more accurate. But at the end of the day, it's a tool, right? It's just like a hammer. You can use a hammer to drive in a screw, but you're better to use a screwdriver for a screw, right? So it'll have the right applications, and it'll have a lot of different applications, but it won't be perfect for everything. And putting the proper guardrails or protections in place to prevent people from getting hurt or designs not going the right way will be the part that we are still learning. So throughout my classes, I encourage students to use AI. I know in AI in education is still a very heavily debated topic, but as you cannot avoid people from using phones or from using hammers, at some point students are going to use it. So I say, okay, you might as well learn how to use it properly, but then always, use it. Use it consciously. I don't know what the drinking age is in your country, but it's like alcohol, right? There's a healthy way of consuming, and then there's an unhealthy way of consuming. So it's the same thing with AI. At some point, you use AI for everything, and then you become a slave to the beast, let's say, and you don't know what the right use is anymore. So where that line falls, that's the part we still have to see, and in the next few years will be instrumental for that. But that's an excellent point to raise. And yes, we are using AI in everything. So
Thank you so much.
Any other questions?
Well, if you do have any questions, I'm not sure how much time we have here, but my email is on the slide here. Feel free to reach out or to Angie or one of the team members here, and they can definitely, hopefully, answer all of your questions.
But Professor, this is a topic that I personally love, and every time that this is not your first time here, and I was already very impressed, and if I could go back in time, probably I would be one of your students. Actually, I'm not very good with the math, maybe going out on the business side or something like that, but it's aviation and aerospace, something really amazing. And I'd like to thank you so much for joining us again, and you'll certainly invited again for future conversations like this with the other students. And I visited University of South Carolina. It's an amazing place, and I think it's really a great place for you to do your studies, not only in aerospace engineering, but in many different fields. And I really recommend you to learn more about the university. We have more materials about the school here, and it's really a place that you should look for. Okay. And again, Angie as well, thank you so much for your time. And I wish you an excellent day. Thank you so much again.
Thank you so much. Hope you have a great day as well.
Have a great day.
Thank you all.
Thank you.
Thank you, Andy.